Today's topic is on the periodic table of the elements. We're going to go through a little bit of the history of the periodic table, and then we're going to look at the periodic table in a little bit more detail and look for some patterns or what's called trends in the periodic table. So to start off, Dmitri Mendeleev was basically, he's sort of known as the father of the periodic table. He was sort of the first one that actually organized 64 of the known elements. He also arranged the elements according to atomic mass. So he put the smallest up at the top and the biggest sort of going down in the rows. And what he did was he found that similar properties occurred regularly. And we basically started to see some patterns. So here was Mendeleev's first periodic table. Okay. And so he noticed that like all of the elements in the first column here kind of behaved the same, in the second column behaved the same, in the third column behaved the same. So that was sort of one pattern that he noticed. He also saw some gaps. So there were some gaps here where right now I have white boxes. And so he predicted that there should be elements in those boxes that maybe were just undiscovered. And he was right. That actually helped us to discover new elements that we had previously not known about. So here is one of Mendeleev's predictions. So he predicted that there would be an element, he called it X, and he called it ecosilicon. Okay, he predicted the atomic weight to be around 72 because of where it was on the periodic table. He predicted some of its properties, its color, melting point, boiling point, things like that. When we actually found this element, we called it germanium. And you can see a lot of the numbers are really similar. So he was able to use these patterns in the periodic table and actually predict a lot of the properties of it just based on where it should be on the periodic table. So that was a really cool thing that he did. Now the modern periodic table is a little bit different. We have more elements on there. And now instead of arranging it by atomic mass, we arrange it by atomic number, so the number of protons. But we still see the same patterns. Similar patterns occur regularly. The first pattern that we're going to look at is a trend in atomic radius. So I'm going to show that on the next slide. Here's a trend in atomic radius. So a trend or a pattern that we see. So as you can see based on the arrows is that as we go across a row, the atomic size actually decreases. As we go down a column, the atomic size increases. So your smallest atoms end up being in the top corner up here where helium is, and your biggest atoms are in this bottom corner. So the general trend for atomic size or atomic radius is that it decreases going across and increases going down. So that is one pattern that you do need to know about. The second trend is in density. So in density, as we go across a row, there's actually no clear pattern. It varies. It can be up, down, staying the same. So we don't see a very clear pattern there. But again, as we go down in a column, it does increase. So that's one pattern that we found in density. A third trend is in melting points and boiling points. So when we compare metals and nonmetals, metals, again, going across, it varies. There's no clear pattern. But as you go down, the boiling point and the melting point decreases. For nonmetals, it's the opposite. As it goes across, again, it varies. There's no clear trend. But as you go downwards, it actually increases. So to sort of show you that, here are some densities of the group 1 elements. So you can see we've got lithium, then sodium, then potassium, rubidium, and cesium. They're listed down a column on the periodic table. So as you can see, as we're going down this first column in the periodic table, what happens to the density? It's actually going up. Here are some graphs of melting points against atomic number, okay? And what you basically see is exactly what I described to you. Now, you'll never ask to be able to draw these graphs, but if I give them to you on a test or a quiz, you have to be able to interpret them. So if we look over here, again, we've got lithium, beryllium, boron, and carbon is all increasing. And then suddenly it drops way down, and all of my melting points and boiling points are really low. So as we go across the row on the periodic table that way, there's no actual clear trend. There's no real pattern. But when we start looking at the groups and going downwards, that's when we see a little bit more of a pattern. So this just kind of shows you how we have no pattern going across the rows of on the periodic table. Okay, so organizing the periodic table, there are a couple of new words that you guys need to know. So I'd like you to fill in these blanks, and as we go through, and know that you do need to know these. So from this point on, instead of me referring to rows on the periodic table, rows are now going to be called periods, and the columns are now going to be called chemical groups or families. So you have to know if something is in period 3, that means it's in the 3rd row. If something is in group 13, that means it's in the 13th column. So you have to be able to know the difference. So remember, rows are called periods. Those are going this way. Columns are also called groups or families, and they go up and down. Elements in the same chemical group, so the same column, have similar physical properties and chemical properties, which is really cool. This means that they react in similar ways and form similar compounds, and this is because they form the same ions. Okay? I have a really cool demonstration to show you guys with the group 1, the first group, those elements, so lithium, sodium, and potassium. I'm going to show you that in class because the way that those compounds react with water as you go down the group is pretty cool. So here are the elements. This was a picture that I was going to show you guys for your unit project. So remember I said part B of your unit project has to do with, I'd like you to use a picture of an element or of what the element does to kind of display and make a class-size periodic table. Here are some ideas for you. So if you want to use the slide, you can pause it, take a look at where your element would be, and you can sort of use that to sort of guide you as to what the element looks like. You don't have to use these pictures because you can see a lot of the metals are just gray and shiny, but there are other things in there that are really cool for you. So that's just another periodic table to show you. Let's go through some examples. Sodium and chlorine can combine to form sodium chloride, which is NaCl, or salt. What compounds do you think are formed between lithium and chlorine? So sodium and chlorine combine to make sodium chloride. What do you think lithium and chlorine would make? You thought LiCl, or lithium chloride? You're right. What about potassium and chlorine? Again, KCl, okay? So we're using 1 sodium and 1 chlorine, we're using 1 lithium and 1 chlorine, and 1 potassium and 1 chlorine. That's because sodium, lithium, and potassium are all in group 1. They're all in the first column on the periodic table. Let's look at question B. What compound do you think will be formed between sodium and fluorine? So now we're looking at sodium, which was the example I gave you at the first, but instead of looking at chlorine, we're looking at fluorine. Now fluorine is in the same group as chlorine, so what do you think will happen? We're actually going to get a similar compound, but instead of having sodium chloride, we now have sodium fluoride. And can you guess what kind of a compound would be formed between lithium and bromine? Again, bromine is in the same group as chlorine and fluorine, so we're going to get LiBr. We're going to look at how to form compounds. If this slide you found a little bit tough and you sort of had no idea where I was going with it, we are going to look at forming compounds a little bit later on, so probably next week. So we will go through this in a little bit more detail, but it's just sort of a preview as to what's going to be coming. All right, let's go through a couple of important chemical groups. These are, remember, the columns. You need to know these ones. So the first one is the alkali metals, and this is the demonstration that I'm going to show you in class. Consists of everything in group 1 except for hydrogen, so you could write that in. They are very, very reactive. They like to form chemical compounds easily, so much so that they do not exist on their own in nature. They're found in compounds. All elements in this group have one valence electron. So the elements that are in this group are, with the exception of hydrogen, lithium, sodium, potassium, rubidium, and cesium, and actually francium too. Okay, if you drew the Bohr-Rutherford diagram for all of them, for sure you guys should be able to draw the first three. But if you drew them for all of them, if you knew how to draw them for every single one of them, the valence shell, so that outermost shell in your Bohr-Rutherford diagram, would only have one electron in it. All right, next one. Oh, sorry. Hydrogen ends up being a group totally on its own because it doesn't follow any of the rules of the alkali metals. All right, the alkaline earth metals, this is group 2, so the ones right beside lithium, sodium, and potassium. They are also very reactive. They form chemical compounds easily, and again, so much so that they don't exist on their own in nature, but instead they're found in compounds. All the elements in group 2 have 2 valence electrons. So the ones in this group are beryllium, magnesium, calcium, etc., etc. Those are the ones that you guys will need to know and draw. And if you drew the Bohr-Rutherford diagram for those 3 elements, again, you would have 2 electrons in the outermost shell. So hopefully you see a pattern. Group 2 has 2 valence electrons. Ooh, look at that. Okay. Let's jump across the periodic table to the second to last group. We're going to look at the halogens. That's in group 17. So here we're talking about fluorine, chlorine, bromine, iodine, okay? So we're going to look at those ones. So we're going to skip the ones in the middle for now. We'll come back to them. These are also very reactive, and they like to form chemical compounds easily. All elements in this group, they don't have 17 valence electrons, but they have 7. So we just use, when it's a double number here, we just use the second number to tell us how many valence electrons there are. They have a very strong smell, and they're commonly used in cleaning products. So for example, I'm sure you guys have heard of chlorine bleach. It's made up of chlorine and other things, but chlorine is a part of that compound. Okay, and then the last group that we're going to look at right now are the noble gases. This is in group 18, the very last column on the periodic table. These gases are inert. That means they are not reactive, they're very stable, and they're quite happy just hanging out on their own. They do not combine easily to form compounds. And the valence shell of each element is completely full. Why? Because it has 8 electrons. Okay, that's where we're going to stop today. We're going to go through some more examples in class, and I will definitely show you that demo of the alkali metals. And in class, we're also going to color in your periodic table to reflect these groups that you do need to know about.